Hello everyone. Today we are going to understand how to name a coordination compound. Now, if you have ever gone through the textbook, you might see a good representation of 9 rules, okay, which are important for the nomenclature. Problem is every time we can't sit and by heart the rules, right? Nobody is going to ask you, give the rules of nomenclature. Rather, people are going to expect you to find out the answer, find out the name, try to formulate a name. The sad part over here is the names or nomenclature of coordination compounds do not run as we have done our IUPAC names. They are a little bit different. Okay, they are a little bit complex in nature. So if you want, you can take a screenshot of these 9 rules that we are going to follow. But rather than just explaining these rules one by one, I would prefer if we could solve some examples and understand what is the basic way of representing or formulating the name of a coordination compound, for which you might require to take a screenshot of this page as well. This page is going to give you a good insight on what names can be conferred to the ligand. Okay, always remember negatively charged ligands are anionic in nature, positively charged cationic, no charge neutral ligands. The good part over here, we do not study cationic nature ligands, rather we are only stuck with anionic and neutral ligands. Anionic meaning you can see over here, Br minus negatively charged, SO4 2 minus negatively charged, ONO minus, C2O4 oxalate 2 minus. So these negative charge carried by the ligands are coming under anionic ligands. Under neutral ligands, you get 4 important examples, that is ammonia. When we are denoting the nomenclature, we do not put it as ammonia, we put it as amine. Please note the spelling as they have mentioned over here. It's not amine, not NH2. It's NH3 amine. Okay. Carbon monoxide, we call it as carbonyl. Okay, my bad. I didn't mention R over here. H2O water, we do not put it as water. In names, we use it as aqua. And ethylene diamine, we use it as EN or ethylene diamine. The best way to represent, you can always write ethylene 1,2-diamine, that would be better. Okay, so these 4 ligands are going to carry 0 charge, they are going to be neutral, whereas these ligands are going to carry a negative charge. Now, the common issue with students is, ma'am, how do we remember so many ligands? Best way, start practicing them using nomenclature. So every time you are seeing a new compound, refer back to this chart. Try to understand what ligand can be used. Do not sit and by heart. That would be the worst way of doing, as well as you would be wasting your time. Okay. So let's jump back to the general representation of any coordination compound. We have something called as a coordination sphere. Now, inside the sphere, generally, we first write the metal, followed by the number of ligands that might be present. Okay, so I'm leaving that as an open session, whether it's a tetrahedral, square planar, octahedral, no matter how many ligands you wish to put. But while representing the formulae, we are always going to mention the coordination complex within the coordination sphere. And always we need to write the metal first in formula and followed by the ligand. Now, the prefix side of this coordination sphere and the suffix side of this coordination sphere, or as we wish to label them as left prefix and right suffix. Okay, no matter what you want to name them. Okay, always remember, we always write a cationic or a positively charged element on the left hand side. It could be potassium, it could be sodium, it could be anything. So if you want to mention such a metal, you always need to write it before the coordination sphere. Suffix is always going to carry an anion, that is negatively charged element or entity. It could be bromine. It could be SO4. It could be anything. So when we are using a cation outside the coordination complex, we are always going to put them in front or before the bracket. And whenever we are using any negatively charged entity outside the bracket, it would always go on the right hand side or the suffix. So this is how we generally represent any kind of compound. Now, if you want, we can just take an example over here. Let me just skip this. Oh, good. We get the first question as an example. So can you see we are looking over here on this compound. This is chromium, NH3 thrice, H2O thrice, Cl3. Now see, the Cl3 is what? It is outside the sphere. Meaning here the role of Cl3 is of an anion, not a ligand. It's outside the complex. How do we represent this then? Chromium would be here. We would be having like 6 coming out. We have one NH3, 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 H2O, H2O, H2O. And outside this coordination complex, we would be having 3 chloride ions. Okay. Let's take one more where we can see any kind of a metal. Oh, we are seeing a cation over here, right? So this is what? Na3 Al F6. So over here, fluorine is the ligand, whereas the sodium is before the complex. So it is bound to be a cation. How do we represent this? We are going to first represent our main complex, which is aluminium, 6 fluorines, 1, 2, 3, 4, 5, 6. And before this bracket even begins, we are going to mention our sodium. Okay, so this is how we are going to formulate a given complex. Now coming back to naming of the complex, let's try to understand this. We have this one compound that we have taken. Okay, so always before you start naming, if you have any cation or anion before or after the complex, I always suggest the students to first separate it. So what do we have? We have 3 chlorine. We know chlorine carries a negative charge. So outside the bracket, we have -3 charge. Okay, outside the bracket, we have -3 charge. 3 chlorines, each giving 1 negative charge. Let's see the bracket. We are left with chromium, NH3 thrice, H2O thrice. Correct? Now, always remember, compounds are formulated in such a way that they always nullify the charge and bring them to 0. Meaning, if outside the complex there is -3 charge, the complex itself would be carrying +3 charge. Okay, so if outside the complex you can see -3 charge of chlorine, the complex itself would be carrying same charge but in opposite magnitude. Okay, so you are bound to get it such a way. Okay, now we know our complex. Our complex is this, and it has a +3 charge. Step number 1 of nomenclature. Always remember, your nomenclature does not directly give you the right to start naming. In coordination complexes, step number 1 is always find the oxidation state of central metal. whichever metal is present in the coordination complex. Over here, we can find chromium to be the central metal, right? Chromium is the central metal. So first thing first, step number 1 brings you to finding the oxidation state of chromium metal. It's pretty easy. If you have followed other lectures, you'll always know. We have 1 chromium. We have 3 NH3. And we have 3 water. And the total charge outside is +3. Let's see over here. If you can find ammonia and water, we can find NH3. We can find H2O, and both of them are neutral. Neutral meaning their charge is going to be 0. Their charge is going to be 0. Meaning we have 1 chromium plus 0 charge of water, and we are getting +3. So we know this totals out to be 0 only. So chromium is equals to +3. Now, why are we finding the oxidation state? Always remember, in coordination complexes, we are bound to mention the oxidation state of the central metal in the name. That too in the Roman numeric form. Roman numeral form meaning what? Like this. So I'll help you out with how nomenclature is done in this case. Okay, we'll start with first. Okay, remember this. Whenever you're writing the compound, metal comes first, followed by the ligand. But whenever you're writing the name of the compound, always make sure to put the name of the ligand first. You give that right or that priority to the ligand. So see, we have 2 ligands over here. We have one that is amine, and we have another one that is aqua. Whenever you're naming the ligands, always name them alphabetically. So A and A, we can't argue over there. But we know that M comes before Q. So we start naming amine first and then aqua. So how many amine? Triamine. How many aqua? Triaqua. Triamine, triaqua. You generally write it in the same line. I do not have space over here. What do we have? We have chromium. See, here comes the other rule. Whenever your complex is carrying a positive charge, your metal should be named as it is. Let me show you over here. Whenever the complex is a cation, what do you mean by complex is a cation? Your complex is carrying a positive charge. So whenever your complex is carrying a positive charge, metal is named same as the element. Whenever complex is an anion, meaning what? Its bracket is carrying a negative charge. Metal ends with the suffix ate. This is important. Here in our case, our complex is showing a positive charge. Our complex is showing a positive charge. So our metal would be as it is. We won't be naming it as chromate or chromiumate. We are going to keep it as chromium. Chromium. Chromium what? Oxidation state 3. Oxidation state 3. Now, no matter how many chlorines you have outside, let them be 3, 5, 10, 100, no problem. You always name it as chloride. That is it. No trichloride, bichloride, tetra, penta, no, nothing. Always remember, outside the coordination sphere, naming is just for the sake of the element. It is not going to represent how many elements of chlorine are present outside the bracket. We are very much invested in understanding what is inside the bracket. So what is step number 1? Step number 1 is to find the oxidation state of your central metal. And step number 2 is to construct the name of that particular complex. I always suggest you split the complex if you have such a compound complex, okay, like you have an anion as well as a coordination compound given. You first separate them. So you'll understand what is the charge on this particular complex. Once you understand the charge, it would be easy to find the oxidation state of the central metal. Okay, now once you find the oxidation state of central metal, naming always begins with the ligands, that too alphabetically. So amine comes before aqua alphabetically. That's why triamine, triaqua. Now, because the complex is a cation, it is a positively charged complex, right? That's why we are keeping the name of the metal as it is, chromium. Okay, oxidation state comes in Roman numerals with a bracket, followed by the name of the anion. So rather you can go through the rules once and then you can start the nomenclature. Or if you're new to nomenclature, you want to understand it better, I always suggest ditch the rules and first start with understanding the names using this video. Once you understand the names, the rules become imprinted in your brain automatically. Okay. Let's see another example. Over here, we have what? We have Ni stands for nickel. Cn is supposedly a ligand. 2 minus. What all things can be understood from this complex alone by looking at this complex alone? First thing that we can understand over here that there are 4 ligands over here. 4 ligands are there and all of them are Cn. We'll see what is Cn. Second thing, there is no cation mentioned before. There is no anion mentioned after. Okay, so you're only given the complex. Third, the complex is carrying a 2 minus charge, meaning the complex itself is considered to be negative. Is negative. And what do we know out of this? Whenever a complex is negative, our metal is going to turn to metallate. Our metal is going to turn to metallate. So let's see how we can understand this. Step number 1, as always. Step number 1 is find oxidation state. Find oxidation state of central metal. Here we have nickel, right? How is this arranged? Nickel, we have got Cn, 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 Cn. And outside the bracket, a mandatory 2 minus, right? So nickel happens to be our central metal atom. So we are finding its oxidation state. We have 1 nickel plus 4 Cn groups and the total charge is -2. Let's try to understand what is Cn. So let's find Cn first. If you take a minute, you'll understand Cn is a anion. It carries -1 charge. It carries -1 charge. So you're going to put it in this particular equation. Anion plus 4 times -1 charge, giving you -2. So Ni minus 4, giving you -2. -4 goes on the other side, you get +2. Correct? So this is how we find out the first step, that is oxidation state of nickel. So how are we going to represent it? We are going to represent it in Roman numeral. Okay, with a bracket, definitely, curved bracket. Step number 2 is the name of the compound. So what's the rule over here? Anytime you name a compound, you should always prioritize your ligands. So over here we have 4 ligands, meaning tetra. But tetra what? Tetracyano. Tetra cyano. So we have tetracyano. Then what? We have nickel. But what is the problem? Here, because of this negatively charged complex, our metal is turning to metallate. So nickel is turning to nickelate. Nickelate what? 2. You can leave this over here as it is. Some teachers might want you to represent it as an ion. You can do that as well. Ion, why? Because there is no suffix or prefix given, so you need to mention it as ion. Even if you leave it at nickelate 2, nobody is going to question you on it. Okay, I hope slowly and steadily you're building upon how to name a particular coordination complex. Believe me, it might take some time. It's okay. It's something new. It's something different from what you have been learning so far. The way we are naming out our compounds, ionic, covalent, whichever compounds we have named, we had a specific way of naming them. Let them even be organic chemistry for that matter. When we were naming hydrocarbons, we had a way. How did we fix ourselves on that way? Because we have practiced it so many times. Here in 12th grade, you're seeing this coordination complex for the first time. You're trying to decipher it. It will take some time for you to understand. So pay attention and please keep patience. Just because दो compounds nahi aaye does not mean that you are not going to understand it anytime. Keep faith in you and let's go to the next compound. The next compound over here we have looks something like this. CO is not carbon monoxide, it's a metal, cobalt. Then we have C2O4 thrice 3 minus. Okay, so we need to know over here how to represent this. Okay, so we are first going to start with oxidation state. So first find the oxidation state of whom? Whom are we finding? We are finding it for cobalt. We are finding the oxidation state for cobalt. So take a minute, try to find the oxidation state. You can pause the video over here, try to find the oxidation state and we'll continue. Let's see. We have 1 cobalt, then we have 3 C2O4 and the total charge is -3. Let's try to find out what is C2O4. If you can find it, we see over here, C2O4 is nothing but oxalate. Oxalate. And what is the charge on it? Charge on it is -2. Charge on it is -2. So let's put that charge over here. We have 1 cobalt. 3 times -2 is equals to -3. So cobalt -6 is equals to -3. Plus 6 minus 3 is +3. The oxidation state of cobalt or the charge is going to be 3. Always remember that most of your compounds, okay, would be having metal, central metal from the D block. There might be some exceptions where aluminium and all can be found. So mostly 98% of the central metals are from D block. So they do show variable oxidation state. Don't be panicked over there. Okay. Now let's try to name this particular compound. While naming, the first thing that we remember is we name or prioritize the name of the ligand. We can see 3 ligands are there. So try. Try what? Try oxalato. Try oxalato. Oxalato. Oxalato what? Cobalt. Now, here comes the thing. If you see the charge of this compound is negative, so the metal turns into metallate. So this becomes cobaltate. Cobaltate what? Cobaltate 3. If you wish, you may put ion over here. Trioxalato cobaltate 3 ion. Okay. Now, you might have seen this table twice or thrice up till now. So what do we need to know? Most of the anionic compounds, okay, would carry a negatively, anionic ligands, my bad, would be carrying a negative charge, and all of them would be ending with O. Bromo, chloro, fluoro, iodo, cyano, sulfato, nitrato, carbonato, hydroxo, oxalato, nitro, nitrato, cyanato, isothiocyanato. But none of the neutral ligands end with O. Amine, carbonyl, aqua, ethylene diamine. So O itself indicates an ionic ligand. Okay, so when we are giving the IUPAC name for a ligand, especially negatively charged ligand, we need to put that extra O. Okay, let's try another compound. We have already separated it. Okay, over here we have a suffix. No, we have a prefix. And prefix is always a cation, meaning it is going to be positively charged. Let's break this down. We have how many? We have 3 sodiums. We know each sodium carries 1 positive charge. So outside the complex, we have 3 positive charge. We know what happens to the complex then. The complex gains the same number but opposite charge. So if it's plus 3 outside, complex itself will become minus 3. Step number 1, find oxidation state of the central metal, that is aluminium. We have 1 aluminium, we have 6 fluorine, minus 3. Let's try to see the charge of fluorine. You can see, we can find over here fluorine. Fluorine has a minus 1 charge, right? So 1 aluminium plus 6 times minus 1 charge giving you minus 3. Aluminium minus 6 giving you minus 3 goes on the other side. Aluminium becomes plus 3 charge. Okay, let's try to hunt down the name. Okay, so here always remember, if you have a cation before the coordination compound, you respect the cation. So we see a cation over here first, right? So we are going to name this cation. Only thing is we are least bothered about the number of cation before the complex. So we are not going to name it as trisodium. We only name it as sodium. Sodium, now we start the complex naming. First comes the ligand. 6 meaning hexa. See now what is fluorine? Again, anion, right? So fluoro. Hexa. Fluoro. Fluoro what? Fluoro aluminium. Right. But problem being, here many people have it out. Because minus 3 is the charge, we know 8 should be coming. Right. So many people have this sweet little doubt whether we call it as aluminiumate or we call it as aluminate. We prefer the term aluminate. Please pay attention on this. Aluminate, charge being 3. Here we won't be putting ion. Why not ION is put over here? Because sodium is present. We have something. We either have a prefix or a suffix. So that time we need not put the charge or ion in the nomenclature. Kindly note, it is not aluminiumate, it's aluminate. So here you need to understand. Now this is not given in any rule book, but this is out of experience that we understand. So we have sodium hexafluoroaluminate 3. Let's go to the next one. You can pause the video, try out the nomenclature, and then you can join back. No problem. Here, first things first, we are going to separate. Okay, so we have potassium, meaning it's before the complex, it's bound to be a cation. 3 potassium, potassium has +1 charge on it. So we have +3 charge outside. Here we have got a complex CONO2 6 times. We know if it's +3 before the complex, after the complex it is going to be -3. So step number 1 being find the oxidation state. Find the oxidation state of cobalt. We have 1 cobalt plus 6 times ligand NO2 and outside charges -3. Let's try to see NO2, right? Yeah, we have NO2. NO2 we can find over here. It is nitride group and has a charge of -1. Correct? So we have cobalt plus 6 times -1 giving you -3. Cobalt -6. 6 goes on the other side. We are left with cobalt plus 3. Luckily, we are getting all of them as +3, most of them. Right, let's start the nomenclature now. Okay, with time, naming becomes fun, naming becomes easy. Since we have a cation, we start with naming the cation first. So we have potassium. Potassium, 6 times, right? So hexa. Hexa what? Hexa nitro. Sometimes we prefer to put the term N. We'll understand why we are doing this. Even if you put nitro, no problem. Okay, it just indicates that we are using N as the donor site, nitrogen as the donor site. Even if you do not put N, no problem. Nobody is going to punish you for it. Okay, then we have cobalt. But since our complex carries a negative charge, it becomes cobaltate. Cobaltate what? Cobaltate 3. So we have potassium hexa N or directly hexa for that matter. Okay. Nitrocobaltate. Okay. Let's try to move further. Next one. Next one. Now we again have an ion. We don't have a complete complex. Okay. So we have Cu NH3 4 times plus 2. Step number 1. Step number 1 is constant. Find the oxidation state of copper. Correct? So we have 1 copper plus 4 times NH3. 4 times NH3 giving you plus 2. Right? Let's see NH3. NH3 is a neutral ligand, meaning it has a charge of 0. So copper plus 4 times 0 giving you plus 2. Copper's charge is coming as plus 2. Let's try naming it. You can pause the video over here, name it yourself first, and then you can restart. No problem. How many ligands do we have? We have 4 ligands. So we get tetra. Tetra what? Tetraamine, not 1 M. We have 2 M. So please make sure you give that feel. Amine. Okay, amine, not amine. Okay. Tetraamine. Now, here you can see we have a positively charged complex, right? It's not a negatively charged complex, correct? So we are going to keep our copper as it is. It does not become cuprate. Copper 2, and if you wish, you can write iron. See, all these names come in one line. I don't have space, that's why I'm writing it down. You can write it in one line, no need to mention your metals down or somewhere. Okay, let's try the next one. Okay, now here we can find that it's split into an anion and cation. So first we'll separate them. Fe, H2O 5 times, NCS. Anything else? Do we have anything else to separate? No, right? So it's just a big compound, that's it. Okay, do not get confused over here. We have just one compound. There is no separation, no cation, no anion. Okay, let's try to do the first step. First step is find the oxidation state of Fe. So we have 1 Fe plus 5 times H2O plus 1 times ligand NCS giving you plus 2. Fe, let's see, we need H2O and NCS, right? H2O we find over here, the charge is going to be 0. NCS is over here, charge is going to be -1. How do we know it's -1? It's given over here, right? So Fe plus 5 times 0, neutral ligand, plus 1 time -1, giving you plus 2. Fe -1 plus 2 goes on the other side, Fe plus 3. Let's try naming. Okay, so we'll start with naming over here. First of all, this is called as aqua. Let's see, okay, let's see. This H2O is aqua. NCS, because N is there, we call it isothiocyanate. Isothiocyanate. So the name would be isothiocyanate. So whenever we have two ligands, we always go alphabetically. Aqua comes first because letter A. 5 aqua meaning penta aqua. You can write monoisothiocyanate. Generally, we do not require you to write. It's okay. It's okay if you do not put the term mono. We understand it as examiners. So we take it as isothiocyanate. Again, I do not have space. That's why I'm going down over here. Iron. Why iron? Why not ferrate? Because plus 2 charge. Plus 2 charge. Now, if you wish to satisfy your teacher's wish, you can go for iron. I hope by now you might have understood how to name. And see, you understood this without even memorizing the rules of nomenclature. It's okay to read the rules, but do not by heart it. Nomenclature is like mathematics. It's okay if you know the rule of mathematics, how to solve it. But each question is going to be different, right? Each numerical is going to be different. So you need to use your brain, understand how to go about it, and that would help you provide a better insight on the rule. Same goes over here with any type of nomenclature in chemistry. You first try to understand it from your teacher, how to name it. Then once you get a rough idea on nomenclature and naming, you go back to the rules. Now it becomes crystal clear what they are talking about the rules. Because if you first go through the rules, you are going to be haphazardly searching, oh, which rule to apply, which rule to apply. And that would confuse you even further. Okay. Let's do another one. Okay, ma'am has got a lot of questions. So we separate it over here. We write PT, PR2, NH3 4 times, And there are two bromines over here. We know bromine carries a negative charge. My bad, it's 2, not 3. Okay, so over here is -2. So the charge over here comes +2. Take a minute, pause the video, try to solve it. What would you get if such a question is given? What would be your answer? Try to formulate. Step number 1 would be finding oxidation state of PT. PT is what? Physical training? No, platinum, right? We have 1 platinum plus 2 bromines, Brs plus 4 NH3s. And we have a positively charged complex, so +2. PT, let's see, we need bromine and NH3, right? Bromine, 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 the first one. -1 charge on bromine. NH3 is over here, 0 charge on NH3. Let's try to substitute. 2Br, meaning 2 minus 1 charge, plus 4. NH3 is neutral ligand, 0, plus 2. So PT minus 2 plus 0 gives you +2. -2 goes on the other side. Platinum is carrying an oxidation state of +4, right? +4. Now let's start naming. We know if we have a suffix or we have an anion after the complex, its name should also come after we have named our primary complex. Okay. So we'll first start with understanding which name to be given. This is what? Br is what? It is bromo. NH3 is what? Amine. So let's try to allocate. We have bromo. We have amine. So A comes before in alphabetical order. So we have tetra amine. 2 meaning di or bi. We prefer di. Dibromo. Okay, since it's a positive complex, we need not make our metal to metallate. We can keep it as metal. Metal is what? Platinum. What is the OS? Platinum's OS is 4. Now, no matter whether there are 2 bromines outside, 8 bromines, 10 bromines, outside bromine is only bromine. And we call it as, if you remember, bromide. No tribromide, no dibromide, nothing, only bromide. And that is it. That completes your naming. Okay, we have one more complex, I guess. We have more complexes. Wow, teacher is pretty much invested for you to learn. Okay. So we have Fe. Now see over here, C and O, both alphabetical. We call it as carbonyl, if you remember. Okay, so first things first. Are there any charges over here? No, there are no charges, meaning charge is 0 outside. If there is no charge given outside and it's in an ionic form, you consider it to be 0. Okay, you can be that much perspective over there. We need to find oxidation state of iron. We have 1 iron and 5 COs. It's not cobalt, it's rather carbonyl. And what is the charge on carbonyl? Neutral here, right? So it's 0. Okay, outside also 0, inside also 0. Okay, poor iron. Okay, oxidation state is 0. Can it be 0? Yes, it can be 0. No problem. Nobody is going to hang you if it's coming 0. Let's try naming it. Very simple name. What is the name over here? How would we name it? Penta, because 5. CO is carbonyl. And what? There is no plus, no minus. So you keep it as iron. And what iron is it? Iron 0. Pentacarbonyl iron 0. Rare question, but yes, in competitive exams asked a lot. It actually confuses the student a lot. We are not used to seeing 0 outside the complex as a charge. So yes, please mark this up. Very important from competitive point of view. In competitive exams, yes, you're bound to get this question. That's a word. Okay, let's go further. I think, yeah, okay, we are on the last question. Wow. Okay, might be a lengthy video here, but I guarantee you by the end of the video, you would be satisfied, you would have understood how to name. Okay, we have two complexes. Again, competitive exam-based question. Let's separate the two complexes first. We have Ag, NH3 twice. We have another complex Ag, Cn twice. Oh, but there is no charge on both of them. What do we do? Okay, we do something really good. We know Cn is what? Cn is an anion. There is a good chance that over here there can be a negative charge. Okay, negative what? If you have no other negatives to consider, you consider it as -1. You can't give it as 0 because Cn itself is an anion. It is bound to confer a negative charge. If this is -1, what does this become? This becomes +1. +1. Yes or no? Okay. So let's try this. Let's try finding oxidation states for both these compounds separately. Find oxidation state of, now, generally we call it as silver, but you know that it is arginate as well. Okay, so let's go ahead. We have 1 silver plus 2 NH3s, giving us +1 charge over here. We have 1 silver plus 2 CNs giving -1. Let's see the charges over here. NH3 carries a 0 charge. Cn carries a -1 charge. Let's substitute. Ag plus 2 times 0 gives you +1. That means Ag is +1 in the first complex. Second complex, Ag plus 2 times cyano compound, right? -1 gives you -1. Ag -2 -1 goes on the other hand, becomes +1. See, best part, both of them carry +1 charge. Let's go to the nomenclature now. First compound nomenclature. First compound we have amine, right? We have amine. What amine? Diamine. Now see, charge is plus, charge is plus. It's a positively charged complex. So we keep our silver as it is. Keep our silver as it is. Let's see the second one. We have 2 cyano, meaning dicyano. Problem being, sometimes people write it as cyano, sometimes people also prefer it as cyanido. Okay, no problem. We generally stick with cyano, not cyanido. In case you see cyanido somewhere, it's not something different. Do not be stressed over there. Now, silverate is not a compound. It is arginate, right? So we are going to put it as argentate. Argentate. Copper becomes cuprate, iron becomes ferrate, arginate becomes argentate. Okay, argentate what? 1. Why is it 8? Why is it 8? It's because of the negatively charged complex. Rarely asked, but yes, seen mostly in competitive exams. Again, a competitive exam-based question. So the last two questions we did before we complete this particular session are very important from competitive exam point of view. We name these two compounds separately, okay, because these are two different complexes coming together. If you have understood this much, I would suggest you can try these 20 compounds. Okay, try them up, try to understand how these compounds are made. In future, let's try to even make a session on discussing each of the 20 compounds. Till then, I hope you have understood a good chunk of how to name coordination complexes. And with this worksheet of 20 sums, you'll be able to ace the nomenclature. Believe me, coordination complexes, once your nomenclatures are thorough, you gain that amazing confidence there. Okay, so make sure you practice more. See you next time. Signing off. Bye.